So now that we know how to excuse me, how to represent surfaces parametrically, we now move on to our main focus here. The main idea is to actually look at surface integrals. Just like we looked at line integrals, now we are in a position to actually compute what are called surface integrals. Just like we integrate over a path C, any function f of x, y, z, we can also integrate over a surface S, any function f of x, y, z. So this is how it's represented, and in the practical calculation, and you'll see now the connection between this and parametric surfaces is as follows, which is that once we have we parameterize the function, of course, and then we multiply this by the absolute value of the cross product of the derivative representing the parametric surface R with respect to the two respective parameters u and v in this case, as identified here. And this can enable us now to calculate surface integrals, in fact. So let's look at some examples. So here is a surface integral, and we want to integrate it over the surface, the sphere, x squared plus y squared plus z squared equals 1, for instance, in this case. So in order to do this, you've seen we have parameterized the sphere before. Basically, our parameterization, we will use the spherical polar coordinates, which seem to fit quite well here. So x equals sine phi cosine theta, y equals sine phi sine theta, and z equals cosine phi. Now, remember, usually we have a rho, so just for your reference, I'm using rho equals 1 because the radius of the sphere here is 1. Okay, and that's what you would do. Suppose it was 9, you would use rho equals 3 in this, for instance, and so on and so forth. So anyway, so this is our parameterization, which means our r is in fact phi theta, and it is as you see it here. So it's sine phi cosine theta, sine phi sine theta, and cos phi. So this is our parametrized. Now remember, of course, we already know that this is a sphere, so phi is between 0 and pi, and theta is between 0 and 2 pi. So next we need to calculate r phi and r theta. So r phi and r theta are as here, and we proceed to calculate the cross product of these two, and that turns out to be, cross product works out to be this, and then we will of course calculate the modulus or the norm of this magnitude, and that will boil down to, you can see there's lots of sine squares and cos squares here, so essentially this is what we're talking about. Let's just do that. So that's just collecting the first two terms here. Cos squared theta plus sine squared theta is going to be 1. So that's going to give us, sine squared phi is common, because this, remember, this is going to be 1, all of this. So just take that sine squared phi out, and you'll be left with, again, sine squared phi plus cos squared phi, which is again 1, so that's just equal to sine phi in the end. So now the surface integral that we're looking for, which is this one, x squared ds, can be written as, of course, with the parameterization, we're looking at, of course, 0 to 2 pi for theta, 0 to pi for phi, and we have to, of course, parameterize. So x is, as you can see, x is sine phi cos theta, so this will become sine squared phi cos squared theta. Okay, sine squared phi cos squared theta, because x, as you'll see here, it's x squared. We have to replace this sine phi cos theta into here, so it'll become sine squared phi cos squared theta, right? And that's this part now we're working at. So we've got our limits for the D. Region D is the surface, basically the sphere, and this is your F, and RU cross RV we already have, which is sine phi. So we'll just plug that in here. So we have sine phi, And of course, we're going to be doing phi first and then d theta. Don't confuse this with the rho squared sine phi, the spherical polar coordinates. So this is not spherical polar coordinates we're using actually. So just need to be careful about that. We are using those, the idea from that, in fact, but we're not. This is not a spherical polar coordinate issue. So anyway, now it's just a matter of solving this integral, which is not rather difficult to solve. It's actually quite simple, and this will work out to be, since these are numerical, the limits are both numerical, so we can actually do these two integrals, iterated integrals, simultaneously, in fact. So we can separate it out. What I mean by that is we can separate them out. Cos squared theta, d theta, and it'll be 0 to pi sine cubed phi d phi. I'm sorry. D phi. So that'll work out as. So this just show you how the integrals can easily be worked out, and then that boils down to just 4 pi over 3 after you do all the simplification. Another interesting little formula I want to show you, it's a shortcut, can make things a lot easier, calculations much easier, is if you have any surface z equals g of xy. So you have a surface g equals z equals g of xy, and you're integrating any function, and you want to find the surface integral of f of xy, z for instance, over this surface, and this surface happens to be this one that I show you here. Then what you can do very quick, is you can check that if you were to calculate the Rx and Rys for this, clearly the parametrization you would use would be x equals x, y is y, and z would of course be g of xy. So your parametrization is essentially xy. Okay, so in that case, if we were to calculate our Rx, so in other words, our R is like this, xy, g of xy. So if I were to calculate Rx, for instance, it would just be 1, 0, okay, partial g by x, and Ry would be 0, 1, partial g by y. Okay, so then the cross product of Rx, Ry would simply be minus gx minus gy, okay, and 1, right? So that's the cross product, and the absolute value of this cross product will in fact work out to be the square root of now partial gx essentially means the z coordinate. So remember, z is g, so partial z by x is partial g by x. So we can substitute that back in here if you like, or you can leave it as it is. Doesn't really matter. But what you'll end up with is, if you like to keep the g, we end up with this, all right, which means our integral, this integral here, okay, it will become, so it'll be f xy g of xy, okay, and then this and dA. So it can be done in this manner. So this is a quick way. You can cut down a little bit of work because the cross product is already calculated for you. So I can show you a quick example of this, of how fast it can work out here. Here's an example. So we want to calculate this integral y ds over the surface z equals x plus y squared. This is a perfect example where so this will work out. We'll use this this formula you see here. So this integral will be equal to directly we'll get into 0. So we'll do y first. So it's 0, 2. X is 0, 1. And the function is y, so y will remain as it is, no change to it. And we'll have the square root of, now this is your g, or if you like, this is just partial z by x actually, and this is just partial z by y like I showed you before. So you're just taking the x derivative, which is 1 squared, plus the y derivative, which is 2y squared, plus 1 dy dx. So you can see how quickly the integral pops out here. Very, very short and quick way to do this. So that'll boil down. We can simplify this to taking the square root out, 2 there, and that just leaves us that. And that will come down to just a very straightforward integral. And it'll work out to be 13 root 2 over 3.